Thank you. Can you all hear me? So thank you for the introduction. And in my brief remarks, I want to briefly speak about the potential use of genetics for type 2 diabetes. Even though we have heard in the first two keynote speeches that type 2 diabetes, the rise in prevalence in obesity and diabetes is mostly due to factors that have changed in the last 30 years, and by necessity that has to be the environment, because genes don't change that fast. The truth is that all those changes are taking place on the background of a genetic predisposition to the disease, and some of that genetic predisposition underlines the diversity that we see, the health disparities that we see between different ethnic groups. So over the last 10 years or so, there has been a tremendous explosion through genome-wide association studies and next-generation sequencing techniques in the ability of investigators to determine the genetic background for type 2 diabetes. And shown in this slide is by year of discovery in the last 10 years, on the x-axis, all the genetic loci across the genome that have been conclusively and reproducibly associated with diabetes, with the odds ratio on the y-axis and the mode of discovery shown in different color. We have over 100 or so loci now known for type 2 diabetes associations, and about the same number for obesity. So the question is, does all this genetic variation that we have now uncovered will lead to changes in the practice of medicine, in prevention, and in policy? One thing that is obvious just from looking at the size of the odds ratios are quite modest. And therefore, what is emerging is that the use of these markers for the individual identification of risk is limited, in part because they explain a very small fraction of the heritability of the disease, but also because we are so good at predicting outcomes based on clinical factors alone. So they don't add a whole lot of information at the individual level to be able to discriminate who is going to get diabetes and who isn't. So what potential uses of this information can be? So the very first one, and I think the slides are out of order, so we go to the previous slide, you see that diabetes is a very heterogeneous disease. It is defined by the common final pathway of hyperglycemia. You can get to a high glucose in many different ways. Of course, we know that type 1 and type 2 are fundamentally different. But even within type 2, there are different subtypes that we don't quite understand and that we treat in a one-size-fits-all type of approach. So the use of genetics is now being helpful in understanding the subtypes that lead you to a more insulin-deficient type of type 2 diabetes, a more insulin-resistant type of type 2 diabetes. And you can begin to stratify people in a way that then might lead to better understanding of mechanism at the molecular level and more targeted treatment approaches also based at the molecular level that departs from the current very common algorithm of one-size-fits-all. One application of this genetic knowledge has been, for example, in diagnostic dilemmas, where, for example, you have a patient where you're not sure whether they have type 1 or type 2 diabetes because they depart from the norm. For example, a young adult between 20 and 40 years old who's antibody positive, suggesting autoimmunity, but obese. And so you don't know whether this is type 1 or type 2. And there's now published examples of how you can use a genetic risk score for type 1 diabetes and deploy it in comparison with a genetic risk score for type 2 and help you in the diagnostic decision for that person who has tremendous clinical implications as far as the treatment. Another example might be in the stratification of the population in groups where interventions may make more sense. So in this example from the diabetes prevention program, one of the clinical trials that Dr. Rogers alluded to, we took participants who had prediabetes and were at high risk of developing diabetes and divided them by their genetic risk score. So shown in the four bars are the quartile genetic risk score with the highest genetic risk to the right, the lowest genetic risk to the left. And in blue are people who were randomized to the placebo arm of the diabetes prevention program with a genetic risk going up with diabetes incidence, as you might expect. But what we showed is that intensive lifestyle modification is able to counteract the genetic risk, particularly in the group with the highest genetic risk. So what you see in the very far right is that people randomized to lifestyle had a tremendous response to diet and exercise that completely overcame the bad deck of cards that they had received through inheritance, providing a very positive message for our patients as far as prevention is concerned, that you're not doomed by your genetics or your family history to develop diabetes, but there's something that you can do. It's the other side of the environmental coin. So those are current uses of genetics in terms of understanding heterogeneity, deployment for diagnostic dilemmas, and stratifying the population where that might be useful. In terms of promises or hope, where I see also genetics playing a role, I think pharmacogenetics is a very pioneering area in two ways. One is in the use of genetic stratification for the tailoring of pharmacological response, so that we provide the treatment to people based on the molecular subtype of the disease that they have. And the second is in the pharmaceutical industry to use genetics for target identification and development of new therapeutics. So that is not completely realized yet, but there are some hopes that that can be the case. A second future use of genetics has to do with the use of genetics to understand causality. So many times we identify some biomarker that circulates in serum, say, or some epigenetic mark that we see associated with the disease, but in these epidemiologic studies you cannot establish causality because there may be reverse causation and you don't know what happened first. If you happen to have a genetic anchor that determines whether that biomarker is up or down because you have the genetic determinants of that biomarker level, and then you can demonstrate that those genetic markers that influence the biomarker also have an effect on the clinical outcome, then you have closed the loop on the error of causality, and you have put that biomarker that you can intervene upon on the causal pathway to phenotype. So that has been used successfully, for example, as a positive control for LDL cholesterol and coronary disease, where the SNPs, the polymorphisms that determine LDL levels, have a clear impact on coronary disease. It has been shown to undermine the confidence in HDL raising being a beneficial mechanism, because the SNPs that raise HDL have absolutely no effect on coronary disease. And we have recently shown that the polymorphisms that determine glucose also have an effect on coronary disease, letting credence to the controversy and resolving it that modifying glucose has an effect, a modest effect, but a discernible effect on coronary disease. And finally, a third potential application of genetics, I think, will be in the design and implementation of more intelligent and rational, efficient clinical trials, where you can then select a population that is enriched for risk, and so you have a shorter type 2 outcome, greater statistical power because you have a higher number of events, and then the ability to tailor the response to the people who have been defined in a more molecular mechanism.
Great. Wow.